background on how semantic search works. The main overview here is the idea is to cover semantic search fundamentals, as I mentioned, in the context of this retrieval augmented generation workflow, particularly for question answering. And so I'm not sure everybody on the call's familiarity with this subject, so I'll start off with just an introduction to what RAG is. We'll spend the bulk of the time then talking about search and semantic search in particular. So we'll do a little bit of a background on traditional approaches to search and information retrieval. We'll go in depth on the basics of semantic search, how it actually works, and then talk about some practical things around it, like how do you actually use semantic search in a scalable way? So different types of indexes, what it means to do similarity search, vector databases, which is a very popular topic these days. And then at the end, we'll talk through some practical ways to actually improve your information retrieval system. So with that, I'll dive in. So why is this retrieval augmented generation paradigm popping up? And so if you think about like what's happened in the past 6 to 8 months, we have these really powerful LLMs that can do a lot of things. They can answer questions really well, and they can meaningfully understand and model general language and can reproduce information that they've seen during training. So if you see on the left here, we asked this question to ChatGPT: I want to make mac and cheese without any dairy products. Do you have a recipe? And it spits out what seems to be a pretty decent recipe without any dairy. And I'm sure this makes some good mac and cheese. And so this does, like, these LLMs have this very good ability to understand language they've been trained on. But there's a lot of things that they don't actually know. And so if you see in this example on the right, which country won the most gold medals in the 2022 Olympics in Beijing, ChatGPT gives you a cutoff saying, I don't have any knowledge beyond this certain date. That date corresponds to the date, the maximum date of which the training data was sourced from. And so LLMs are really good at a lot of things, but they lack the ability to reason about information that wasn't in their initial training data set. And so, yeah, if you zoom out, LLMs are good at understanding language. They're pretty good at following instructions. They're capable of basic and even in a lot of cases now complex reasoning, and they can understand code. But areas where they fall short is knowledge of current events. So things that happened after their training data cut off, they're not very good at, or they have no tangible knowledge of. Knowledge of your proprietary data. So if you have domain specific data or nuanced information that isn't a large part of the general corpus on which they were trained, it's going to struggle there. And yeah, nuanced domain specific topics. So that begs the question then is, okay, how can we use these powerful LLMs with this reasoning ability to unlock and use information that's stored within specific knowledge bases upon which it wasn't originally trained? And so this is kind of like the leading question into this field of retrieval augmented generation is, how do we use the benefits of LLMs and what they're good at for data that they don't have any understanding of? And so there's two main approaches for how you can do this today. The first one is this idea of fine-tuning an LLM on your knowledge base. And so at a very high level, the way this works is you have a model that gets pre-trained on some very, very large, diverse training data set. And so this is, to do this pre-training, we're talking thousands of GPUs, over trillions of tokens of really diverse data, training on the scale of months, weeks to months. And this is raw text, just doing next token prediction. And I don't know, anywhere from 1 to 10 to 15 to $20 million to pre-train one of these large foundation models. And so the idea then is, okay, you take this foundation model, you have this generally capable general knowledge LLM, and you take your specific knowledge base then, and you just continue the pre-training. You fine tune this generally capable model on your specific data. And this is on the order of 1 to 100 GPUs billions of tokens roughly. It can be measured in hours to days of training and a lot more accessible from a cost standpoint, thousands of dollars maybe. And so you do this process of fine tuning and you end up with a model that you can now ask a question to about your specific domain, and it will auto-regressively generate you an answer from its distilled stored knowledge. So it'll regurgitate out um, high probability sequences from this fine-tuned knowledge that it has that is on your specific information. And this is fine, like this works. But there are quite a few issues with this. The first one being that there's no source clarity. So if you just have an LLM that's just you ask it a question, it's just auto regressively generating you text from its learned weights. It's first of all going to be really prone to hallucination. So it's going to be prone to making up facts, making up things that sound real that are otherwise not. And there's also no distinction between this idea of like what was generally available knowledge and what's specific knowledge. It's all just kind of blended together, and the LLM is just decoding based on this blended knowledge. So you have no way to like really pinpoint where the knowledge is coming from. The second issue is this idea of no access restriction. So if you had the case where maybe some of the users of your LLM should be able to access certain information or invoke certain information out of the LLM, whereas other users shouldn't be able to get answers to certain types of questions. If you have one fine-tuned model, there's no way to tease this apart. Basically, I mean, you could try to include some system prompts and based on a user, say, don't answer questions about this, this, or this. But that's really janky. It's not going to be a reliable solution. And basically, any users of that LLM are going to be able to pull out information, any information they want that the model has been trained on. There's also the technical overhead considerations. So fine-tuning models, curating data sets, training the models, and then actually hosting, maintaining, and serving them can be a daunting task. There's a lot involved there. You need the right talent, you need the right team. Some companies don't have that. And then finally, one of the biggest ones is this idea of the need for fine-tuning repetitions. Basically, we live in a dynamic world. The information that we in the areas we operate is changing all the time. There's net new information, and there's also updates and edits to previously known information. And so basically, if you do this fine-tuning approach to get your LLM to know something about your domain, anytime there's a change or an update, you need to refine-tune, retrain that model to reflect those changes. And so this could be an ongoing issue that you constantly have to be keeping up with. So for all these reasons, fine-tuning might not be the best approach to introduce domain-specific information or current events into your LLM's sphere of influence. And so the second option then is to basically include any domain-specific relevant data that you have inside of the context window of a generally trained LLM. And so that's what we see here. We'll see that we ask this same question of which country won the most gold medals in the 2022 Olympics in Beijing. And we provide it with a paragraph or several paragraphs of context from an article about the 2022 Winter Olympics. And we prompt it to answer the question given this context. And we see that the model is able to get it right. And so this is the general idea behind retrieval augmented generation is we take advantage of LLMs for what they're good for, which is understanding language, following instructions, and basic reasoning. And we leave the domain-specific part to this augmented context that we provide. So this tees up kind of the scenario for how we're operating here. And so one interesting way to think about this idea of retrieval augmentation, this is actually a slide from one of Andre Karpathy's recent talks on the state of GPT, which is a really good talk. I would highly recommend if you haven't seen it. And an interesting way that he frames this is like, so on one end of the spectrum, you have this idea of traditional search. So type in a query, get back a list of results. You manually have to read through them to understand what's in each one and how it could possibly answer your initial query. On the far other end of the spectrum is this idea of LLM memory only. So you ask a question and you just get some randomly regurgitated answer from the LLM that best tries to match what it's learned during training. And so this retrieval augmentation sits somewhere in the middle. It really makes use of the best of both worlds and gives you this hybrid approach that can be really, really useful. And so the emerging recipe for how this works, I'm sure some of you guys are familiar with this. It's pretty straightforward, but the general idea is that at query time, or sorry, prior to query time, so before you actually go to use the system for answering questions, you break up all the documents in your knowledge base into chunks, and you compute this embedding representation for each chunk and store it into some type of searchable vector database. And then at query time, so at the time that the user is trying to actually get questions answered from your system, you take the question, you compute an embedding for it, you use that embedding to search for relevant pieces of information from your stored vector database. And then you retrieve a few of those, combine the question along with that retrieved information and format that into a prompt. That prompt then gets passed along to the LLM, which serves as the reasoning engine to get your answer out. And so this is kind of like a very high level schematic of how this technique is evolving. And really there's two main components to it. This actually goes back to like traditional question answering from NLP before we had these powerful LLM decoder models, where you have this retrieval component, which is to narrow down your search space, get back just a few documents. And then this reader component, which previously used to be extractive question answering and is now abstractive, so generative methods. But the reader actually is what processes those retrieved documents and gets you the answer. And so for the rest of this workshop, we're going to primarily be focusing just on this retrieval component. And it's really important that we do so, or that people pay attention to this, because at the end of the day, if you're asking a question and you're using an LLM to reason over the documents that were retrieved, or I should say, your question answering system will only, in this setup, will only ever be as good as the documents that get retrieved and passed to the LLM. If you ask a question and the LLM gets provided documents that don't even contain the right answer to the given question, there's no way you can expect the LLM to actually provide the right answer. So this retrieval component is actually often underlooked and really crucial to the overall performance of these types of systems. All right, so let's get into the information retrieval then. I guess teeing this up, like semantic search is a relatively new concept. There's a lot of hype around it right now. It's a very popular and growing field. And so I guess the first question is like, why is there all this hype around it? And so one way to explain this is there's this benchmark called the Trek Robust benchmark in information retrieval. And it's basically a benchmark to measure the performance of different information retrieval methods and systems and approaches. And you see this this dark line here represents a benchmark model that was developed back in 2004. And you'll see that since 2004, there's all these non-neural methods, all these red dots. And then even like getting into 2016, 2018, a few neural-based methods, so dense learned based methods that even over this span of whatever 10, 15 years haven't done much better than this initial method that was developed back in 2004. And so there was kind of like in the world of information retrieval, there's kind of like a stagnation in progress until the advent of the transformer architecture, which came about in 2017 with the paper Attention Is All You Need, and quickly started, like it was originally developed for machine translation and then quickly became broadly applied to every area of NLP, including information retrieval. And so that's where you see in the past 3 to 5 years, transformers being applied to search, to information retrieval, and breaking this stagnation in progress, getting much better performance on traditional benchmarks with the application of transformers to this new field. And so I guess let's first talk about like what is this traditional approach that has been so good for so long. And it sounds like you already are pretty familiar with the idea of lexical search or inverted indices and BM25. But the general way that traditional search has worked is that you find relevant documents based on syntax. So literally matching, given a query, look for explicit word or n-gram overlap between the query and the documents you're searching for. And so this is often referred to as lexical search, keyword search, bag of words methods, and also called sparse methods for retrieval. And this is the underpinnings of how Elasticsearch works, like you mentioned, or things like Apache Lucene or Stolar. They all work basically in the same way of matching terms. And so the algorithm that's used under the hood is BM25. It's basically a modified version of term frequency inverse document frequency, if you're familiar with that from traditional NLP. But at a high level, basically what it tries to do, there's three main components to BM25. The first is term frequency. So the idea is that the more appearances of a search term the more appearances that a term in the query appears in a document, the more relevant that document should be, which makes sense. Weighted by this inverse document frequency. So the more documents there are in the corpus that contain a search term, the less important that search term should be. So like in this example here, you see words like a or in or the. These are very commonly occurring words. And since they occur in just about every single document in your corpus, those terms shouldn't be heavily influential in ranking relevant documents. And then the final component is field length. So if you have a short document, so short in length, and it contains a search term, that search term is more impactful to that overall document than if it was present in a much longer document. It has a higher weight in the document. And so these three components together make up BM25. And this is as I mentioned, this is the underpinnings of how search has worked for a long time. And so while it has worked really well, there are a few very important challenges to this approach of search. And so the first one is that this idea that exact wording is critical for producing good results. And the reality is that there's often a difference between the words that are used in a query, so the words that I use to actually search for something, versus the words that are used in the results that I want. And this whole idea boils down to the idea that semantic lexical search, BM25, fails to capture semantically related ideas. So things like synonyms, acronyms, and variations in spelling. And so if we look at this example here, we have a query, a 2-bedroom brick house in Los Angeles. Say I was searching for that. And there was a document in the corpus that said a stone residence with 2 rooms in sunny LA. Well, you and I, like, we know that this context should be a good result returned for this query because they're talking about basically the same thing. It's a very relevant result. However, if you were scoring this context for this query using BM25, it would actually have a very, very low relevancy metric matching score. And that's because we have a synonym here. So brick versus stone. It's a synonym. It's a different form of the word. And so we wouldn't get a match there. Los Angeles versus LA, they mean the same thing. They're different versions of the same word, but lexical search would completely miss the match here. And also variations in spelling. And so 2 and 2, again, different forms of the same meaning that would get lost. And so that's one major issue. Another major issue is this idea of context being ignored. And so this is really what semantic search is all about, is this idea of context. And so if you take this example here where we have a query where a user types into the search engine, learn Python, and you have these two documents in your corpus, learn 5 fun facts about Python snakes and Python programming tutorial. Well, again, we know that this user is searching for most likely some programming tutorial. They want to learn about Python scripting or development. But context one is actually going to be returned as more relevant because it contains the word learn and it contains the word Python, whereas context number two only contains the word Python. And so we would actually get a poor result in this scenario as well because of the need or the dependency on token overlap. So two high level issues that point out some of the flaws with traditional search. So that leads us to, okay, this more modern method of information retrieval, which is semantic search. And the general idea behind semantic search is to match relevant documents based on meaning rather than syntax. So you might have heard this referred to as neural search, vector search, semantic similarity, or sometimes called dense methods for information retrieval. And the idea here is that we leverage an embedding model. So we'll get into what this actual model is in a bit. But for right now, we basically leverage this embedding model that can produce these dense representations of these dense semantically meaningful representations of text. And we can compare those in some latent vector space. And so you take the general idea here is that you have a whole bunch of documents in your corpus, you pass them through your embedding model and you get out different vectors. They're collapsed to 2 dimensions here, but typically these are much longer vectors. And then you get your search query and you also put that into the same vector space. And then you can compare the query to each of the documents and see, okay, which of these have the closest distance in vector space. And as long as you have an embedding model that meaningfully encodes semantics, the closest vectors in vector space are going to be the most semantically similar documents. And so this is the general idea behind this newer approach to search. And so the natural next question is, okay, well, what is this embedding model? How does it produce these semantically meaningful vectors? And so that's where we need to look at what is an embedding. And so embeddings are those dense vectors, those semantic representations, and they're abstract, so they're not really interpretable by humans directly. They're learned and they're dense. So if you think about a way, like if you think about how you can represent a document in numeric form, one way you could do it is you could take a vector of length vocab size. So here we have there's roughly 30,000 words in the English language. You could take a vector of length 30,000 and have a binary encoding for each position in that vector if the word in that position is present in the document. So this is one way that you can represent a document in vector form, is just a binary encoding of every element in the vocab. And this is indeed how methods like TF-IDF vectorization work. And you end up with this very sparse representation. You can imagine that like in a given tweet, let's say you're going to represent tweets, there's, I don't know, maybe 100 words. At most, you're going to have like 100 Boolean toggled values, and the rest of them in this 30,000 vector are going to be very sparse. They're going to be empty. So you end up with this like sparse representation of information. Embeddings, on the other hand, are this learned dense representation, and the vectors themselves contain floating point numbers. They're much smaller in length because they're encoding this rich information about a given word or document. And so it's a more compact and rich way to represent information than these traditional sparse approaches. The cool thing about these embedding vectors is that they encode semantic meaning. And so, like one of the classic examples, this is from the Word2Vec paper, the idea of Word2Vec back in 2014. Whereas if you have word embeddings, these embeddings, you can actually do this, you can do vector math on them, and they relate to the vector math actually coincides with our human understanding of what those words should mean. And so the classic example is if you take the vector for king and you subtract from it the vector for man and you add the vector for woman, you will end up in vector space very, very close to the vector, the learned vector for queen. And so this ability to do vector math and this ability to have relationships that encode and retain computable semantic meaning is a really important idea and is the basis for semantic search. The last way to think about this is like if you were to cluster words based on their, if you were to cluster words based on their vector embeddings, you would find that words related to similar topics all cluster together. So here you see that like vectors embeddings for food items would cluster together, and for sports would cluster together, and for school would all cluster together. So these vectors respect and maintain this semantic relationship that is interpretable to humans, is the idea here. Okay, and so on the last slide, we saw that we have these vectors, so these embeddings for words. So on a word level, you have a dense representation of what each word actually means. But for semantic search, we don't want vectors for each word. We actually want a dense embedding for an entire sequence of words. We want embeddings for an entire sentence or paragraph or chunk of text to encode. And so how does that work? Well, we'll take a high level look at how transformers operate. So the general idea is that you have, for a transformer to encode information, you first have, so you have your text input, you split it up into tokens. Those tokens get looked up in a dictionary basically to get retrieve back a unique ID, integer ID for each of the tokens that retrieves an embedding. Those get passed through the encoder, and the encoder actually learns dense representations, contextual representations for each token. So basically, this vector that you get out of the encoder naturally is going to be a contextual representation of the word my as it exists in this sentence along with all these other words. So it's a word embedding that's specific to this word in this exact sentence. And so this is just naturally how transformers work. Encoders naturally output this hidden state, which is also known as contextualized word embeddings, which are a vector for each word in the input. But what we really need is a single vector for this entire sequence here. We want one dense vector that represents this whole input. And the way that we do that is to develop these sentence embeddings is through an architecture called a bi-encoder. And so bi-encoders were first really came about in 2018, 2019 with the SentenceBERT package and paper. There's a library for it that's really useful, but there's a paper by this guy Niels Reimers who used to work at Hugging Face actually. And the general idea here is that we can learn, well, let's talk first about the structure. So the way that we get these one vector per input is by training a bi-encoder. And so you see that we have what's called a Siamese network. So we have two pathways in this network. Your query, so a query string and a document string go through a transformer. And then there's this pooling operation that actually does mean pooling. So it averages down all of these contextualized word embeddings. And that pooling operation is what's responsible for getting us out an individual vector. And you see that the query goes through the transformer and pooling, to get a vector. The document goes through the transformer pooling to get a vector. And then these two vectors, these one-dimensional vectors, can then be compared with cosine similarity to understand how similar they are or aren't. It's important to note that in this architecture, so this is a Siamese network, it's easier to depict it as two separate pathways, but in reality, this transformer and pooling layer are actually the same. These are shared weights. So you could think of this as, you could actually do this independently. You could do the query through the model first and then the document through the model first. It's just often easier to visualize it as two separate pathways in the network, even though these are actually the same transformer and pooling layers. Any questions on this before we move on?
No.
Okay. So yeah, here's another representation of the same idea, just turned sideways. You have two sentences, they go through an encoder like BERT. You get out this matrix of contextualized word embeddings, and then there's a pooling operation. So mean pooling is the most common way to do this, where you go from 512 by 768 down to a 1 by 768. And the transformer, along with this operation here, is learned during training. And so that's probably the question now is, okay, well, like we have this architecture that's capable of producing one vector per sentence. How do we actually get it to produce meaningful vectors that semantically hold relevant information? And so I guess the question then is like, how do we actually train this bi-encoder model? And so the way this works is that you have to have a labeled data set. So you have labeled documents where you have a query and a corresponding context document and a label that indicates one for yes, these are similar. Yes, this document does satisfy this query, or a zero for no, this document does not satisfy this query. And so there's a bunch of data sets for this. A very common, famous one is from Microsoft, this MS Marco data set. And it's 5,000 or 500,000 actual search queries on Bing, along with relevant passages that were retrieved for that query that were manually verified as satisfying the query. And so with that, you have a labeled data set. You have ground truth examples of what is a relevant document for a given query, from which the model can learn this idea of relevance. And so basically to train this model, for each of these labeled examples, you pass the query and the document through. At the beginning of training, you're going to get these vectors out that when compared, let's say at the beginning of training, we take a query and a document that are intended to go together. The document does satisfy the query. It's a ground truth label of 1. Early on in training, we're going to put it through the transformer and pooling. We're going to get out a U and a V that when compared with cosine similarity is probably going to come up with a loss that's very small, is very big. Early on, these vectors aren't going to mean anything. And so early on during training, ground truth examples that are similar will have high loss. And so there'll be some error there that can be used to back propagate and update the network to learn this relationship between similarity. The way that this learning is done is there's a few different common loss functions for this. Probably the most common and easiest to understand is contrastive loss. There's also things like triplet loss and hard negatives, but we'll stick with contrastive loss. And again, the general idea here is, so imagine these are documents, not signatures. If you have a positive pair, so a pair that belong together, so a ground truth label of 1, you're going to basically train the model such that if it outputs vectors that are far apart in vector space, and it is a ground truth positive example, we want to force these closer together. And so the loss in this example is actually the distance between them, is your distance here. And then conversely, if you have a labeled example where they are actually different. So the query and the document that is going into the training example are ground truth of 0 are actually different. We would expect the embeddings for them to be pushed further apart in embedding space. And so this is what the training process does, is it uses this contrastive loss function to minimize the distance between embeddings for positive pairs and try to maximize the distance between embeddings for negative pairs. Um, um, okay, so yeah, so that's at training, and then at test time, you can obviously pass through a query and a document, get two vectors, and get a similarity score, or you can just pass through your query or your documents, get out a vector, and store that vector for similarity computations later on. Okay, so I think we're all good here. The cool thing about embeddings and this idea of learning dense representations is that it's not limited to just text. And so if you guys are familiar with the model clip from OpenAI, the general idea here is that as long as you have an encoder that can take in some modality of data and generate a dense vector from it, if you all you need to do to develop these similarity embedding models is to have labeled data of some kind. And so in this case, for the clip paper, they basically scraped the web and pulled back web pages. They pulled back image tags from HTML. So you have your image, and then along with it, you have the alt tag, which describes the image. And so right there, you have a labeled data set of images and corresponding descriptions of them, and that's your ground truth data set. And so they trained a model that basically embeds images and text into the same latent space. So you can do these same similarity calculations, these same similarity operations across modalities. And so if you look in vector space, you would end up like the sentence two dogs in the snow. The embedding for that would end up very close to the image of two dogs in the snow. And then the same thing with the same phrase in multiple other languages. And so you end up with the ability to have these universal representations of data independent of what their actual modality is. So you have the ability to directly compare different types of data across modalities, be it text, images, audio, video. It's kind of this universally shared latent space in which you can do comparisons, which is a super useful thing. And that's, I'm sure you guys are familiar, but that's basically how a lot of modern recommendation engines work. So your product recommendations on Amazon, your movie recommendations on Netflix, and song similarity and song representations on Spotify. So one question you might ask then is, these dense models are really effective. They have a lot of benefits to them, but how do they compare to these traditional benchmarks, these traditional methods like BM25? And so there's been a few benchmarks. The first comprehensive one was the beer benchmark. I believe this was in 2019, 2018, something like that. And basically what they did was they set out to evaluate multiple different methods for information retrieval across a variety of dataset domains and also tasks. So tasks being like retrieval versus classification versus whatever it may be. And so one of the findings, one of the takeaways, some of the results from the benchmark were that, so here we have this dense model. So TAFSB is an embedding based model. We have BM25, and you see that on MS Marco, so on the data set that the dense model was actually trained for, so in domain, it was a held out test set, but in-domain data. So the dense model is trained on MS-Marco. And on this data set, the dense model performs significantly better than BM25, like an 18-point difference, showing that these dense models are very effective. But we also see that for two other data sets that are considered out of domain, so using the dense model that was trained on MS-Marco and using that for retrieval on these two biomedical data sets, we actually see that BM25 outperforms the dense models, and in one case by quite a bit. And so what does that tell you? Like, what are the takeaways here? The main thing is that, first of all, like BM25 is pretty good. It requires no training and it generalizes well. It does its job. There's a reason why it was the standard for a long time. And so it actually performs better on 10 out of 18 of the benchmark data sets. Dense models, like we see here, are actually really strong as long as you're in domain, as long as you're using them for data of a similar distribution as to what they were trained on. And in which case they can be much better than BM25. And then, yeah, I guess the other takeaway there is that dense models struggle with out of distribution data. So if you train a model on one area, if you train a model to work in a domain of X, its performance won't be nearly as good as if you try to apply it somewhere else. So that begs the question of, okay, well, how do we know what embedding model to choose? Like, what is the right embedding model for a given use case? And there are lots of embedding models. I know you guys are already familiar with this, but maybe some others on the call aren't. There is this MTEB leaderboard. So this massive text embedding benchmark is another benchmark that happened a couple of years after the beer benchmark. And basically, there's this leaderboard here that breaks out different models and how they perform across different tasks. And so the idea here being that, like we just saw, you ideally want to, if you can't train your own model, you want to find a pre-trained model that is going to be highly performant on both your task and your domain, like the types of information that your data set is going to work on. So like if you had you guys work in a legal domain. I don't know if there's any legal data sets on this benchmark, but I'd have to check. But the idea is you'd want to choose a model specific to that has demonstrated high performance on your task and domain. And there's lots of models, like we talked about earlier this week. Like there's new ones coming out all the time. These GTE models just came out 2 weeks ago, and the BGE models last week, and they've shown higher performance and are much smaller than some of the other models. I know you guys are using, I think, the instructor model, which is massive. But yeah, so general rule of thumb here is if you're not training your own, fine-tuning your own embedding data, your own encoder model, your own bioencoder, then best practice is to find a general purpose model that performs well on your task and data set or domain. And yeah, there's going to be lots of considerations, like obviously latency, cost, the size, the ability to self-host. All things will factor into your choice of model. Oops. That's embeddings. That's a rundown on how, at a high level, you train them, how they work, how bioencoders work. So the next thing is to talk about, okay, well, what do you do with those embeddings in a search setting? And so we'll talk about indexes and similarity search first, which is, I guess the first thing to point out is that similarity search is a very basic task that can be achieved in 3 lines of NumPy code. There are lots of fancy methods and these vector databases, which we'll get into, but it's good to point out that at its core, this is really all semantic search, similarity search is with dense vectors, is you have your query vector, so a 1D NumPy array of dimension of your embedding, call it 512. And then you have a matrix, a 2D NumPy array that represents your knowledge corpus, all the documents in your searchable corpus that you want to be able to search over. And that's a shape number of documents by embedding dimension. So 512 in this case. And then the idea here is that really all similarity search is just simply a dot product. So you just take the dot product between your query vector and all of the embeddings in your searchable corpus, transpose it first, and then you just simply sort these. This dot product is going to get you back a vector of similarities. You can sort that vector for and then retrieve just the highest top k similarity scores and return the indices. So in a nutshell, like these three lines of code are all you need to do similarity search in NumPy, and this will work as well or better than any fancy method you have, because it's doing exhaustive search. And so basically, like you are exhaustively searching your query against every query that's in your corpus. So like I said, this will work perfectly well for you. This is all that the bigger, fancier methods are doing. The difference here is that obviously this is working in memory. And so as your knowledge corpus scales, as you go from thousands to hundreds of thousands to millions of documents, it's not necessarily going to be feasible to store this NumPy matrix in memory. And so that's where once you get above, I don't know, 100,000 to a million vectors, like anything below that, like it's quick enough and exhaustive search will be the best thing you can do on smaller purposes. Once you get above 100,000 million documents, you're going to have latency trade-offs because one, you might not even be able to fit those matrices in memory. And then two, to actually do this matrix multiplication is going to become, there's going to be a latency associated with it to the point where it will impact the ability for you to use it in application. And so, yeah, the whole point of this slide is just to boil down at the lowest level, like this is really all you need. But when your corpus scales, you need other solutions. And so that's where we get into the idea of indexes and embedding indexes. And really what these are just data structures that allow us to do, instead of exhaustive search over 10 million vectors, we do an approximate search, so approximate nearest neighbors. And there's lots of different algorithms for this. There's flat indices, local sensitivity hashing, there's hierarchical networks, inverted files. The thing to know here is like there are trade-offs for each of these, and you can configure them for trade-offs between quality, speed, and memory. So obviously, now that we're not doing an exhaustive search over every vector in the corpus, there's going to be a quality degradation. We might miss searching over certain parts of the knowledge base that contain the actual the best, most relevant results. But as a trade-off for that quality, we are able to efficiently search over the partitioned corpus in a much faster and efficient way that makes it usable for production use cases. And so there's lots of implementations of these indices. There's nothing necessarily special about certain indices versus other ones. Like there's different approaches that, like I said, have trade-offs. And the indexes themselves are largely open source. And so like, I know you mentioned that you guys are using FAISS from Facebook. There's a few others that are open source. HNSWlib is a popular one, Annoy from Spotify. And these are free open source data structures that enable similarity search efficiently. But these are just data structures. They're not like a database. And so they're not going to come with all the fancy things that you would typically benefit from traditional databases, like hosting, features to be able to store data and metadata alongside the vectors. A lot of vector databases have the ability to do hybrid search across sparse and dense methods. There's going to be no like there's no built-in scaling or reliability or redundancy, any of that stuff. And so when you get to a full use case, you're likely going to want to rely on some database that handles all of those nice to have features for you. I think you guys mentioned that you've experimented a bit with Weaviate and Pinecone. I'd say that those two are probably the most popular now, Weaviate being open source, which is nice. I think this space is very new and changing and growing very quickly. So I wouldn't say that I have like a strong hard preference for any of these over the other ones. I think there's different features that make that might make me more amenable to your use case. But on the whole, they all do the same general thing, which is store vectors, implement approximate nearest neighbor search, and do hosting for you so that you don't have to handle all the intricacies of hosting and serving a database. So we've talked about all the basics for information retrieval with semantic search. We've gone through embeddings, how important your embedding model is, indexes, and vector databases. And so I guess practically, one next question is, okay, well, we're getting X performance, how do we improve it? How do we make it better for our system? And so there's a whole bunch of methods. I'm going to cover a few of the more common options here. And I think I mentioned this on Monday as this particular first option here on Monday, but we'll go in more detail now, which is this idea of using a cross encoder for re-ranking. And so we talked about biencoders, which are basically just encoder models that given a piece of text, get you a dense vector representation. Cross encoders, and so in biencoders, you have like your query and your document are passed through the model separately, individually, independent of each other. Cross encoders take a different approach where you actually pass the query and the document into the transformer at the same time. And it basically reframes this idea of similarity from a cosine similarity vector comparison to a classification problem. So given a query in a document, classify how similar these are or aren't. And so it's a uniquely different paradigm than the bioencoder. Oops. And it's actually extremely effective. Like it works much better than a bioencoder does. And the reason being is that in the cross encoder, since you're passing in the query, which is this yellow part, and the document, which is the green part, you're passing that all in at once. And so it allows the transformer's self-attention mechanism to apply across both the query and the document. The tokens from the query can attend to tokens from the document, whereas with the bioencoder, you only ever have query tokens attending to query tokens and document tokens attending to document tokens. And so this method of cross encoders is like I said, it's really performant. It's very powerful, but it's not without limitation. The primary limitation being, well, there's a couple, but the first one is that since you're now passing in a query and a document together, and you have a fixed context length, your documents have to be much smaller potentially to be able to fit them into the fixed context window. But the bigger issue actually is the fact that there's no embedding that comes out of this. You get a probability score. And so you can't pre-compute document embeddings, which means that if you want to use a cross encoder to search over a corpus of, let's say I have a query and my corpus is 100,000 documents. In order to do that search process, I would need to run a forward pass of the transformer for every single document along with that query. And so this is massively inefficient. And it makes this method completely unusable for large scale search. And so like one of the common examples that's given in one of the early papers is if you were to use a cross encoder to cluster 10,000 documents, it would take you 65 hours, while the equivalent process with a bioencoder or an encoder-based model would just take 5 seconds. And that's because the comparison piece is done purely with just a dot product. So you're just taking um, a matrix multiplication of all of the stored pre-computed embeddings versus with a cross encoder, you have to run that forward pass for every single one. And so a common workflow is to combine both of these, get the best of both worlds, where you use some type of either a bioencoder or even BM25, like a traditional method, to basically take your large corpus and of maybe call it 1 million documents and do a good breadth search first and get return back for a given query, maybe the top 100 or the top 50 most similar documents as determined by semantic similarity, and then re-rank those in a separate stage of the pipeline using a cross encoder to get just the top 5 or the top 3 best hits. So basically, a two-stage pipeline that combines the best of both of these methods. And so if we look at that same study, the beer benchmark that we saw before, we see that on the right here is our bioencoder only method, so dense embeddings with semantic search. Here is BM25, so traditional search plus a cross encoder, and then just BM25. And you'll see that across all of these data sets, some of them being out of domain, the bioencoder, like dense embeddings, perform the worst. BM25 performs slightly better because, again, it generalizes better to out of domain data. But the BM25 plus a cross encoder actually gives you a significant performance boost. And so this idea of this hybrid approach is actually really useful. There's definitely some overhead. It's a little bit more complicated to implement and operate, but it is a very powerful and promising way to get better results if you're trying to eke out some performance. And so another way to look at these results, this is again the same study, is so we have on the x-axis here, these are a bunch of different retrieval methods. So we see that we have our dense method here, and we have BM25 plus a cross encoder, our retrieve and re-rank here. And then on the y-axis, this is number of data sets that did better or worse than BM25. And so you see that this hybrid traditional plus cross encoder generalizes really well to out of domain. It does better than BM25 alone on 16 out of the 18 data sets, while this dense embedding, just your regular bioencoder method, only does better than BM25 on 8 of the 18 total data sets. So the thing is this step here, like I'm showing you BM25 plus a cross encoder here because this is what this benchmark used. This is just how they evaluated it, just to show. This is just demonstration purposes. In reality, you probably would want to use a dense method. You probably would want to use a bioencoder here rather than BM25, or a hybrid of the two, like I said. But again, this is a hyperparameter that you'd have to play around with and get some evaluation metrics out of to see what works best. Cool. Okay, so that's option 1 for improval, which is this idea of retrieve and re-rank. The next option, which I think was asked about earlier, is this idea of domain adaptation. Like, can we adapt some of these pre-trained embedding models to our specific text domain? We saw that if you're using bioencoder or a dense embedding model that's trained on one domain and you're applying it elsewhere, there's going to be noticeable performance degradation. And so the idea here is simply just, can we fine tune these models to our own domain? And so the answer is yes. It largely depends on if you have labeled data. So if you have examples of a query and known relevant passage for that query. So you have a data set that looks like that. It's actually really straightforward to fine tune these embedding models. There's scripts that are readily available. It's pretty straightforward to do. The reality is that most people don't have this labeled corpus, and it can be expensive, time consuming, and tedious to actually generate yourself. And so in the case that you don't have labeled data, there are a few methods that are, I would say, somewhat researchy experimental, but are proving to do pretty well. In particular, this TSDAE, so an autoencoder, which is, I think, mentioned earlier, in combination with this generative pseudo labeling. And there's a lot of, I think, research going on here and benchmarking, but and I won't go into detail on how these work or why, and we could do that at a later time if you guys want. But just the general idea here is that if you have labeled data, you're going to get the best results. If you don't have labeled data, there are options. They're a bit more involved, and your results won't be as good as if you had labeled data, but it should still give you a boost. And then I guess the third option for improving, and there's lots more than this, but some novel approaches that take advantage of generative models. And so there's one approach here it's called doc to query. This is a couple years old now. But the general idea here is that like it tries to pull on the thread that queries and documents, like the nature of a query versus the nature of a document that you're searching for, look rather different. Like queries are often shorter and have different terms than what your passages that you're trying to search for have. And so there's methods like this where you basically at index time, so when you go to actually embed all of your documents, you take the document and you pass it through a generative model that attempts to generate a hypothetical or predicted query. So like, what is a query that this document would satisfy? So now you have some language that is more similar and representative of what queries for this document will be. And then you actually concatenate those together, and then embed this concatenated document into your index. And so now when you actually go and search, you're going to be searching over an embedding that includes semantic meaning from potential hypothetical questions that would have been asked of this document, not just the document itself. And so the idea here is that it's fully unsupervised. Like you don't need any labeled data. You're using a generative model to get you some boost. It's expensive at index time because you need to do this generation process for it before you embed every document. But at query time, there's no latency issues. And then similar to that, doc to query is a newer one called HIDE, or hypothetical document embeddings. And it's similar, but the difference here is that the generative piece is actually done at inference time rather than at index time. So the way that HIDE works is that a user writes basically inputs a question, and you take that question and you use a generative model, a generative LLM, to generate hypothetical documents that might answer that question. And then you actually, rather than embedding the question to search, you embed those hypothetical documents and use those to search over your corpus of documents. And the idea here is that while the hypothetical documents that get generated might not be 100% accurate, the process of actually embedding these documents kind of distills out some of the noise. Like it's a lossy process, and so you're capturing just the semantics of it, but the details aren't as important. And so the idea is that these hypothetical documents will actually be more similar to your real documents than the question would have been to your real documents. And again, fully unsupervised, you have higher expense and at inference time in terms of latency because you have to run this generative model, but they demonstrate that you get pretty good results, a pretty good performance boost by doing such a thing. And I should mention, there's a good blog post with a whole bunch of other approaches that take advantage of novel LLMs and novel ideas to how to get some performance out of your system without having to actually have labeled data to train on. Last thing, just some final thoughts, just for like how to practically go about this. Um, when you're trying to improve retrieval, it sounds like you guys have already done this, which is awesome to hear because a lot of customers don't necessarily think to go to this first, but it's really hard. There's no way to tell if improvements to your system, be that a better embedding model, be that retrieve and re-rank, there's no way to tell if there's actual improvement happening from those by just subjectively like, looking at some examples. Really, what you need to do is to develop a test set of gold standard examples and use some type of like structured evaluation. So use um, run your system, your search, develop a baseline, run your search system, and calculate quantitative metrics for that, whether it's uh, net cumulative discount or some of the like recall based metrics. But basically, just like some hard metric that you know that if I make a change, I ran a baseline, I got this score. I then made an improvement to my system, tried a different embedding model, whatever it may be, and I can quantitatively assess that yes, this did actually improve performance or it made things worse. Um, and so just sounds like you guys are already doing this, which is awesome to hear, but structured evaluation experimentation is super important and often not the fun part, but definitely necessary. Um, and that's all I've got. That's I think we've got